Good. So recording it, and the other one is recording. So let's start one of the lowest levels of classical natural language processing applications: edit distance, minimum edit distance. This technique is applicable to many one-dimensional problems such as this. Okay, the idea is this. Okay, if somebody types these letters GRAFFE, what do they mean? Do they mean giraffe? Do they mean grail? Do they mean graft? Which one? So of course it depends on the context, but ignoring the context, maybe we should make a decision based on this principle. I should choose out of these valid words, correctly spelled words, the one that requires fewest keystrokes to modify this word into this one. That's called minimum edit distance. Okay, how many letters should I insert? How many letters should I delete? How many letters should I replace? Okay, if the amount of modification is minimum, that we call minimum edit distance. So I need to calculate the edit distance between this and this. Okay, if you do it in a stupid way, straightforward way, the edit distance between this and this is erase all of them: 1, 2, 3, 4, 5, 6 deletions and 4 insertions, total of 11 actually, right? But this is very stupid. I don't have to do that. Why? Because I know that the first 3 letters are common. I keep them as they are, and in fact this one is common too, so all I need to do is just 2 delete. Okay, that's one thing. How about this one? The first 4 of them are common, and I need to replace F with a T and delete E, so it is just two modifications, etc. So how do I calculate the distances between these? Okay, so I mean, erasing all of them, erasing some of them, inserting in between. So I need to find a way of doing this. I need to do this in a fast way. So this is called edit distance, and it is good for measuring the how similar two strings are, and it is not used only for the edit distances between one correctly typed and one incorrectly typed words. It is used in many cases. One of them is the computational biology. Suppose you have the DNA sequences of 2 different samples, and you like to know the differences between these 2 DNA sequences. Again, I need to find the edit distance. So it looks like this T is extra, but where is my green? Yeah, this AG and this AG, and in fact AGCTAT, this part up to this part is common, right? Up to this part is, did I miss it? Yeah, this part is common. I think there is a difference. Okay, let's look at this one. So it looks like this part overlaps and this part overlaps and this part. It is easy to see after they are done this, right? So there is a insertion, there is a deletion, 2 deletes, 1 replacement. Okay, 2 deletes, 1 replacement. So I like to do this for a very long DNA sequence, 2 of them. Once you do this, you will say that these are the common parts of the genes, okay, and these are under some modification, some change, and that's a valuable information for these, okay, computational biology people. It is used in there too, okay, and many other places: machine translation, information extraction, speech recognition, etc. And we are going to do this for edit distance, the distance between two two words. Okay, so minimum edit distance between two strings, two different operations available for us: insertion, deletion, and substitution. Okay, I need to transform one into the other. Here is one example. Let's say I have intention, okay, and I like to measure the distance between this intention and execution. So what is this? From intention to execution, I has to go away, so there is a deletion, there is a substitution, n has to be substituted with this, t and x substituted, I keep the same, I do this insertion, substitution, these are the same. So 1 delete, 3 substitution, 1 insertion, that's the distance, total of 5. But substitution is usually more expensive, right? For the substitution, I need to erase one and insert one. So if this is 1, 2, 2, 1 and 2, if I add them up, the total is 5 plus 3 is 8. Edit distance between these two is 8. Well, I was lucky in here because these two words are very similar to each other. You might have said, why don't you insert, yeah, why don't I do that? Insert these three, yeah. I'm going to insert these three, and this E is going to match here, and delete these three now, and replace this one. So what happened? Is this good? No, well, just a bit. Okay, here.
So you have 3 insertions, 3
Delete the first three, keep the same, insert this X, E, and C, and replace. So this is 3, cost of 3 is here, cost of 3 is here, and 1 substitution.
Again, 8.
It is 8, yeah, it is 8. So there are many ways of doing this, but I am after the minimum edit distance. It looks like I am not going to find anything cheaper than 8, right? So let's do this. Let's try to find the minimum edit distance between given two words, regardless of their length. It could be very, very long, because remember those DNA expressions, there are hundreds of letters in them. Okay, so if I do this in a brute force way, it will be expensive. I like to do this in a smart and fast way. Okay, we already did that. This Levenstein, okay, Levenstein way of doing things is that he says that substitution costs 2, so the cost between these two is 8. Delete, substitute, insert, and substitute. Okay, so one of the first method that I'm going to look at is brute force way of doing things. Again, this is a very common problem. With many areas of science and engineering. One of them is the computational biology. This area is growing very fast and big because they have lots of data, right? They are producing lots of data. Previously, they used to produce gene data, okay, genome data for species, for human beings, for frogs, for, I don't know, for worms and anything. Nowadays, they are producing this data for individuals, for individual people, okay, for this person and that person and that person. So each data is terabytes of, each person produces terabytes of data like this, and they have to be kept in somewhere and they have to be analyzed. You need lots of artificial intelligence based stuff for this one, and they are growing very fast, and whatever you do, you are helping the human health, okay, and it will be very useful and lots of money in it, and lots of advantages to be gained for the nations and for the societies. So we have a very nice bioengineering department right over there, okay, and we are interacting with them too for example, the graduation projects and that kind of stuff. I suggest you go talk to them too, Okay, I like to do graduation project with you, and they can advise you, and maybe we can do some joint projects with them. Erdoğan Hoca is working with them very actively. He has graduate students, they have PhD students and master's level students, and we are planning on a common joint artificial intelligence program. I think they are going to contribute that too. So, computational biology, I'm not saying that they are using NLP techniques, but they have one-dimensional data most of the time. NLP sentences are one-dimensional too, right? The languages. It's not like video data. Video data is three-dimensional or four-dimensional. Image data is two-dimensional, at least two-dimensional. But natural language data is one-dimensional, basically, fundamentally, which is almost the same as the computational biology. That's why these kind of techniques are applicable for both areas. What else? Yeah, this is a good example too. Machine translation. I like to know how good my translation is, but no two different translators will translate the same sentence in the same way. Let's look at the first sentence and the second sentence. Spokesman confirms senior government advisor was shot. Spokesman said the senior advisor was shot dead. The meanings are the same, right? I can translate it in both ways. I like to find the edit distance between these two sentences. If they are close, then I will say that my translation, this is the robot translation, this is the human translation. I'm going to say that there is only this much edit distance between them. So I keep the same. This is substitution, insertion, same, deletion, same, and insertion. So 2, 3, 4, 5. The edit distance is 5 modification between two. Not bad. Okay. So I have another. If I have another algorithm that does the translation for me, I would measure the edit distance between the human translation and the robot translation. And the best yet is, I would make another human translator to translate. I would make another human translator translate the sentence, and I would measure the edit distance between these two human translators. It's not going to be 0, right? They will do it in a different way. And I will say that between human H1 to H2 distance is 7, and H1 to robot 1 distance is 8. These are comparable. I am doing as good as human to human differences, right? So I can use this edit distance in these kind of cases too. Named entity recognition, again, extraction entity car reference. These two things are IBM Incorporated, or IBM refers to the same thing. The Stanford President John Hennessy, okay, or the Stanford University President John Hennessy is the same thing. So if the edit distance between these two clumps of words are small, then they mean the same thing. Okay. So I hope I motivated you a little bit about this edit distance. Let's move on. Let's do the first brute phase of doing this state space search. My starting state is intention. My final state that I like to reach is execution, right? So at every step, I can do one of these 3 things. I can delete one letter. This one deleted one letter. Okay. I can insert one letter. So what would I do? I would insert the first letter of execution here, or I can replace this I with an E. Out of 3 things, I can do one of them in one path. So what can I do in here? I can delete N. I can then insert an E at the beginning, or I can substitute N with an E. So 3 possibilities are there too. So tell me the height of this. What would be the maximum height of this 3. How many levels would there be if I do it in a stupid way?
The log of length of intention plus.
No, there are no logs. I mean, if you do the logs,
Height.
intention is already 10 words. If you take the log, it is just 1.
Length of first word and the
Plus the length of the other one, right? So length of intention. So this most stupid way is just delete all of them and insert all of them, right? So delete all of them, insert all of them. It is, what is intention? 6, 9, 10. Let's say 10 plus 10, 20. I don't like that solution. I mean, if I explore this state space, I have to produce all 10, 20 levels of information. That's not going to be good. Okay. The smart thing is that I produce this level, and I produce the second level, third level, fourth level. When I come to fifth level, I will see my solution. Execution will be there, right? Execution will be there, and I will say that, okay, at 5 steps, I can solve this problem. Okay, I'll solve this problem. It seems easy, but how many nodes do you have to produce to get to the fifth level? How many nodes do you have to produce? Okay, 1 node, 2 node, 3 node.
But what do you insert? You can insert anything.
No, when you do the insertion, you insert the first letter or substitution. Remember, I am trying to get to the execution. So don't try to insert anything. Just insert the smart ones. So at every step there are 3 options only: delete, insert, or substitute.
3/5.
Yeah, 3 to the power 5, which is, I don't know, it is expensive. This is 27. 25 times 5 is 125 times 5 is close to 800. 800 nodes just for this stupid edit distance. 800 nodes I have to produce, and this is the best I can do without producing all. By the way, 800 is only the number of nodes at the lowest end, right? So the one previous is, so it is 800 plus 125 plus 27 plus 9 plus 3 is there. So it is more than 1000 nodes, which is not good. So state space search is not good. Maybe you might say that don't produce all of them. Be smart, use an heuristic, and etc. No, we can do better than that. Okay, we can do better than that. Instead of doing it naively, we are going to use edit distance approach. Okay, edit distance is this. We are going to principle of optimality, you know that, right? The dynamic programming. If you know the optimal shortest path between Istanbul and Hakkari, okay, any path between Istanbul and Hakkari is the optimal path between those cities. If the path to the Hakkari, city of Hakkari, goes through Ankara, okay, you cannot go to Ankara using a different way, in a using a shorter distance. So if this is Istanbul, if this is Hakkari, if this is a path to the Hakkari and it goes through Ankara, Istanbul, Ankara, and Hakkari, okay? If this is the optimal path between Istanbul and Hakkari, the optimal path goes through Ankara, then the optimal path between Istanbul and Ankara is this. You cannot have a better alternative than that. And optimal path between Ankara and Hakkari has to be this one too. You cannot find any cheaper solution, because if you have a cheaper solution between Ankara and Hakkari, okay, then I would replace this green one with this red one. Then okay, I have a new optimal path between Istanbul and Hakkari then, right? So dynamic programming does that too. So that means what? if I keep finding these kind of optimal subpaths, and if I add them up, I am going to find the optimal path between Istanbul and Hakkari. Okay, so use this idea for the minimum edit distance. So what am I going to do? I am going to, instead of finding the edit distance between intention and execution, I am going to find the edit distance between subwords of it. For example, if for the first two letters, okay, what is my first two letters? Okay, yeah, between I and E, what is the shortest distance between them, or what is the minimum edit distance between them? It is easy to solve, and I solve it. It is just deletion, that's it. Okay, after I solve this problem, okay, after I solve this problem between I and E, then I am going to solve this problem. Okay, what is the shortest distance, okay, or the minimum edit distance between in and X, right? Well, why am I doing this? I am doing this because while I am solving this blue problem, I am going to use the data that I have already built for this red problem, right? I have already solved it, subpath, okay? Now, after I discover that there is two substitutions for this, I am going to now solve this green problem, okay? To solve the green problem, I will make use of the data that I produced for the blue problem, okay? So it looks like I am not, at every step, I am not multiplying it with 3. I am just adding 3 to it, right? 3 plus 3 plus, so it's going to be much cheaper than 3 to the power, what was the solution? 3 to the power 5. Yeah, 3 to the power 5. Well, we were lucky in that case because execution and intention is very similar words, right? They are very similar words. If the words are not similar, then I would have to go all the 10 levels of it. It was going to be 3 to the power 10, which is very, very expensive. Which is very, very expensive. So expansion is always bad. In this case, it's going to be small. So let's see how this happens. Let's see the algorithm first, and we are going to come to it later. Okay. So I have two strings, x and y. Okay. X is of length m, n. Okay. Y is of length m, and we define a table, dij. What did I say? Dynamic programming, you build some kind of a table all the time. One-dimensional, two-dimensional, three-dimensional, usually most commonly two-dimensional tables. Our table is dij, okay? What does the I and j represent? Okay, they represent the edit distance between the first I characters of x and the first j characters of y. So d11 is the edit distance between I and E, intention and execution. Okay? So D22 is the edit distance between I and in and EX. It goes that way. Okay? So when I am done, when I fill in this table, my solution will be at this top. Okay? D and M. The edit distance between these two strings. Okay, good. Any questions? Let's look at the main algorithm actually. Where are my annotations? Let me clear those annotations. Okay, so dynamic programming, a tabular computation of D and M. The name dynamic programming comes from the original inventor of it, Bellman, in 1950s maybe. Okay, and why he chose it, I have a small slide I am going to show you in a few minutes. Okay, so there's the definition: a tabular computation of D and M. solving problems by combining solutions to sub-problems. We started from the sub-problems and we are moving up and up. Okay? We compute dij for small dij, then we increment ij by 1, and to calculate that new dij, we use the previous solutions. Okay, we compute the larger dij based on the previously computed smaller values. That's called dynamic programming. Okay, so this is the algorithm. It might seem a little bit, what would I say? It might seem a little bit complex to understand, but it is not actually. Let me draw the table actually. Let me draw the table myself. This is the table. Okay, intention and execution, right? I would write, okay, start, this is execution. I didn't have space, I am going to stop it here. And this is the intention. Okay. So let me put, oh no. At the beginning there is 0. Okay. So indexes start from 0. Okay. So this one says that initialize all these I0 and 0j to I and j. So this is 0. Let me put these, okay, sharp signs here. So this is di0 I, this is 1 2 3 4 5 6, and 1 2 3 4 5. From intention to execution we are going that way, right? So what does that mean? This means nothing. This is null. To convert null to null, I need 0 cost. Right? Come on, I thought that would be enough for, I forgot my, what should I do? 6%, 15 minutes. I had 26. I had 26% when I came in. What should I close? Should I kick out all the online people? Online people. Online people, are you there?
Yes.
Don't use any oxygen, okay? Don't hold your breath. What? I mean, I am not using any.
Maybe we can close the camera.
Yeah, just take this camera out. And turn my camera off. Can you still see my slides? Guys? What? I did not. Can you see my slides?
Yes.
Okay, so they see it. Okay, you hear me, but you don't see me, you don't see my pictures. Okay, I hope this will take, I need 15 minutes. Let's see. So I did that. What is the cost of converting a null to null? It is 0, of course, right? What is the cost of converting a null to 1? 1. Sorry. What is the cost of converting a null to E? It is 1. Just insertion, right? What is the cost of converting a null to X? It is 2. I have 2 insertions. Similarly, what is the cost of converting an I to a null? It is 1. Just deletion. So if I go right, I am inserting something. If I go up, I am deleting something. How about this? How about this? If I go this way, what am I doing? What am I doing? But if I go that way, I am substituting, right? I am substituting I with E. So what should I write here? Why? Because they are different, right? Okay. Because they are different. So how did I come up with 2? Because they are different. Because It is one deletion and one insertion. In fact, this 2 is 1 plus 1 or 1 plus 1 or 0 plus 2. How about here? What should I write here? It is like this. What is the cost of converting an I into EX? So if I go to the right, I am just inserting something, right? So here, what is it? I converted this I to an E, right? This is what that means, right? I already converted I to an E. Now I like to convert that I to an EX. I can do that. I can do that by inserting anything. So insertion is just 1, so it will be 3, right? 3. So this 3 is 2 plus 1 here, or I could do that, right? I could do this way. I converted null to EX, right? And I am deleting I here. So I converted this one. So I keep filling this in. How about this one? I am converting this IN to E is going to be 3 again. How about this place? Let's do this. How about this place? Converting EX to IN is going to be again substitution 4, right? 2 plus 2 or 3 plus 1 or 3 plus 1. Okay. So let's do some interesting place. Can I get some interesting place? Okay, this is going to be 4, I guess. This is going to be what? EX and T 5. This is what? E, okay, this is 4. Is that correct? 4. Come on. That. Okay, this is going to be 4. Why? Because 3 plus 1, and 2 plus 2. Okay, and is here. I'm trying to get some interesting place here. This is going to be 5. This is going to be 6.
The one above it will be interesting.
Yeah, but for that one I need to come from here, right?
Okay.
Oh, okay, this one is interesting too. What is the cost here?
2. 3.
It is 3, right?
Yes.
It is 3. Why? Because I don't need to do the substitution. So if I come from here, not that, like that. Okay. If I come from here, it's going to be 3 because this was already 3. This one is already, maybe I didn't write it correctly or readable. Okay, 3. Well, I am not adding 1 to 4, right? Because I am not doing any deletions I am not doing any deletions. I am not doing any insertions. I am not doing any substitutions. Okay? So 3 comes 3. Okay? Because this E and this E is the same. How about this place? It's going to be X and E is going to be what? Okay, tell me what is 4 or 6? 4. Why? Because 3 plus 1 is 4. Because I am going to come from this direction. It's not 1. It's like, okay. So you will run, right?